Okay, today's lecture is going to be investigating primes and related ideas in more detail, and I've assembled a bunch of really nice links, so I'll just go through them relatively in order. The first link is from a site called primepuzzles.net, which is links to the following. Problems and puzzles. Now there are some links here, for example, on records. They have a page, sort of a list page, so you can look at 20 lists dealing with primes and arithmetic progression, very specialized primes like Fermat primes, Mersenne primes, primes I've never heard of, Sophie-Germain primes, primes that are just less than a power of 2, like Mersenne primes. There's generalized Fermat primes, twin primes, etc. So these are links to various sites that you can explore. Some of these, under the conjecture sites, we know are open problems. For example, Goldbach's conjecture, which is, his original one said that every integer bigger than 5 is the sum of 3 primes. Euler then turned that around and said that that's equivalent to the following statement that every even integer larger than 4 is the sum of 2 primes. So there's the even and the odd version of the conjecture, and there's also some generalizations. Now in this particular site, various people work on these, and if you make a little improvement into understanding of the conjecture, they post it. So for example, they state that so-and-so, Matty Sinisalo, has checked the conjecture up to 4 times 10 to the 11th, and then they have a citation of the paper. Another fellow reached, you can see the primes up to 10 to the 13th. And then there's some generalizations called the SMART, S-M-A-R-A-N-D-A-C-H-E, Smarn-dash, I would guess, conjecture. Now there's some other ones that we've seen before, like the twin primes conjecture, saying that there are an infinite number of pairs of primes, p plus or minus 1. An interesting one is the Fermat prime. These are primes of the form 2 to the 2 to the m plus 1. And it is not known whether an infinite number of these primes or not. So some of the conjectures are still open. Are there infinitely many primes of the form n squared plus 1? So there's a guess or a conjecture due to Hardy and Littlewood that the number of primes of that form n squared plus 1 less than n was asymptotic to square root over log n. Now if we move away from the conjectures, which are the really hard open problems, you can move back into the link of more or less amateur problems, and that have actually had significant contributions by essentially not professional mathematicians. So there's one by Pomerantz. It's an observation. His observation was that if you have a prime equal to n minus p, is a prime only for the case n equals 210. So he asks, is there another number greater than 210 with the same property? So then they actually form the variance of the question, and then some of these have actually solutions. And it has to do, I guess, in part with the observation that 210 is the product of the first four primes, 2, 3, 5, and 7, and that has something to do with it. There's a conjecture due to Erdős in here. And then probably the most intriguing ones are the simplest. These are the puzzles. And this particular site posts a puzzle every week with solutions. So there, as you can guess, quite a few puzzles. There are almost, well, there are 218 listed in this site. So for example, 216 primes in a square array. Most of these come from just sort of playing around with primes. So if you want to generate primes in an array such that the rows, columns, and diagonals are distinct prime numbers. So for example, this prime, 113,607,773, can be written as a square array. 113,607,773, these are all primes. Plus if you take the rows, the horizontal rows, which are these, if you take the vertical rows, which are these, and if you look at the diagonals, 103 and 307, all of these are primes. So the question is, can you find a 10 by 10 square array? Or it asks if can you find an extremely large solution, which they call a Titanic solution, which is bigger than a 32 by 32 array. So here is a 10 by 10 array of primes, all of which whose vertical, horizontal, and diagonal elements are all primes. Don't ask me how you would go about finding such a number. And here is a 33 by 33 array of primes. So he eventually, I guess, did it by trial and error, 16 hours to find a 33 by 33 solution. There's another 10 by 10 solution. So all these 10-digit numbers are distinct reversible primes. So if you reverse it, they're also primes. Very interesting. Okay, so going between observation and actually constructing an algorithm or a theory is quite intriguing, and there's probably as many people playing around with prime numbers as anything else in mathematics these days. So there's a lot of links on this site. There's a site also related to prime numbers. It's sort of like a collection of sites. So the numbers in parentheses have to do with the number of links. So there are 51 links to programs to enumerate primes, 117 links to the theory of primes, 22 links to lists of primes, 22 to visualization, etc. So if you look under programs, you can download various sieves, which are general programs that work by eliminating multiples of small primes. Programs to find small primes. Now, a small prime is defined as less than 10 to the 200, so less than 200 digits. Then there's problems for large primes, and I'll actually show you how one of those works in just a bit. So there's lots of links there. I might draw attention to the third link, and that is, this is sort of an amazing formula. This is a formula. Remember we said that there was no polynomial formula that gave prime values for all integer values of n. That actually is true, but there is a formula in multiple variables, namely this one. This is a formula, it's actually a GIF, I can't highlight it, but if you look at this formula, and if you substitute integer values for all the parameters, namely A, B, C, D, E, F, L, M, N, O, P, there's Q's, K's, Y's, X's, T's. I mean, there's a lot of variables in here. I think there's like 21 or so. This takes on only prime values. Now, you might wonder about that because you see this written as a factor, k plus 2 times this curly bracket. So how can the product of two things be a prime? Well, the answer is if one of the factors is 0, or if one of these factors is non-zero, the other is 0. There's also two other representations for a prime. This is a formula where the absolute value here means greatest integer not greater than a. So if you plug in a number x into cosine squared times of pi x minus 1 factorial plus 1 over x, this gives the value 1 if x is a prime and 0 if it's a composite number. So if you have a lot of decimal digit accuracy, you can calculate this number as an indicator function of a prime. This function was then actually generalized into this function, which is the formula for the number of primes, well, the nth prime function. But it's obviously not a polynomial. Okay, so there are actually closed formulas for primes, but when you get large values, they just take too long. It's easier to do it by a sieve method or a Fermat little theorem type method. There's some more links to primes here, link number 4. And this has some of the more interesting links. One of the more interesting links here is autism and primes. Now, autism is not a well-understood psychological property, but it has occurred that, here we go. So we're going to play a little game here and say, how many people think that 1001 is a prime number? Raise your hand if you think 1001 is a prime number. Raise it high because I'm going to count. So 4, that's unanimous. So we'll click on yes. Oh, it's factored 7 times 11 times 13. Let's do the next number. Is 1003 a prime? How many people raise their hand? 1, so the vote is no. It's factored 17 times 59, so no, it's not a prime. How about 1007? Raise your hand, yes or no? Yes. Yes? Yep, 19 times 53.
I quit.
1009. Yes or no? Prime. It is a prime. 1013. Is it a prime or not? Yes? You're right. 1019.
Yes.
Right.
Woohoo!
We're broken even. Yeah, just basically randomly guess yes all the time. We'll probably hit 50%. 1021. Okay.
Yeah.
Here's prime.
If you don't count the first 4.
1027.
No.
Okay. 1031.
Yes.
Here's the prime. We're better than 50-50. 1033. Yes?
Thank you.
Here's prime. Hey. Let's go with the intuition. 1037. Wrong. We'll do one more. 1039. No. Yes or no, prime. 1039. Here's prime. Okay, so we hit 50-50. This is linked, well, the only link between this and autism is the following comment out here. There's a very intriguing book called The Man Who Mistook His Wife for a Hat. A true story, by the way. And inside this book, which is just a collection of people whose visions of reality are just different than everyone else's, there are twins, John and Michael, who were able to define prime numbers up to 20 digits very quickly. However, they had a lot of problems with just basic addition and subtraction. So something within their perception allowed them to tell whether numbers of 20 digits were prime or not, but they couldn't add, simple numbers. So this has sort of led people to wonder whether there were algorithms for determining whether numbers were prime that, are just undiscovered. There's primes in music. There's an interesting thing in here. I think it was primes in DNA sequences. Let's see. Is that in here? Let me look under DNA. Nope. But there was an interesting, okay, let's do the primality testing effort. You can actually put in a number here and it will tell you whether the number is prime or not. So let me just sort of randomly press down some keys, making sure that it's an odd number that doesn't end in 5, say. So is this a prime or not? What's the vote? Yes or no? 50-50, right? Nope, it factored it. So let's test that. Nope, it's not a prime. It's in the form 6x minus 1. So if you can put in some various things that will test your algorithm here pretty quickly. There's aesthetics of prime number sequences. That was an interesting site. See, we could get a link here. Primes and nucleotide bases. Yeah, that was the. Okay, so this site is a site which will convert primes to DNA. So if you want to find out whether you can create a frog or something from a prime number, I guess you can submit this. We'll just let you go on for more links there. This is a particular software. Let me go to this site first. Given it's a French site, as you can see if you read the screen. So it says if you agree with the stupid and insulting American French bashing, or if you want to boycott French products, disconnect now. This site is French. So to go to the download page, which is the next link, you can download a piece of software that's called Primo, which is a very fast prime algorithm for determining whether numbers are prime or not. Now I've actually downloaded this and run it, so I'll show you how it works. Okay, this program called Primo version 2.0.1 is a primality proving program that actually does one more step. It actually gives you certification and verification. So what it does is if you open a file, so let's load a file, and it's of a particular form. So I'll load one I've already done, test1.in. Let's open it. Okay, so this is what the file looks like. It's a plain text file. The semicolon is a comment, followed by a blank line, followed by the keyword candidate, followed by the word n equals, and then a number. So this is just a notepad editor. So this is a long prime, or actually not a prime, I should say. This number was actually taken from the RSA site. So going back to the RSA challenge site, RSA 576, there's a $10,000 prime, and its status is it's not factored. So if you click on it, this happens to be exactly the number that I cut and paste into this. So if you look at this number, and you load it into Primo, so you click on the certification, then you load a number, test 1, it says that basically this candidate is not a strong pseudoprime with respect to base 2. Now, if you go through the help on this program and under certification, what you'll see is that it goes through some well-defined tests to determine whether a number is prime or not. So there's the strong pseudoprime test. This is type 0. So assuming that n is less than 34 times 10 to the 13th, if n is a strong pseudoprime to the base with respect to those bases, then n is a prime. Then there's the n-1 test, n+1 test, and elliptic curve test. The elliptic curve test is one of the ones that does not rely on modular arithmetic as much as the other ones. Now, if you generate a certificate, what it does is it tells the results of whether it's a prime or not, gives the test, and any parameters that are needed, so that you can basically take that number, apply the test with the parameters, and immediately verify whether it's prime or not. Basically, it's like giving the factor of the number, it tells you it's not prime. So you issue what's called a prime certificate. Now, if you go back to the site, eventually you get back to the site. And going back to the site, there's the current record of generating a prime of 5,878 digits long. You might wonder how long it took. A fellow had an AMD XP 1800 plus processor, and he ran it continuously for 22 weeks, and it generated a prime certificate. Now, what this will tell you is that it's a prime or not, but it doesn't necessarily tell you the factorization. If you could do the factorization, then you could do all the RSA numbers and be $500,000 richer. So, in fact, the certificate itself is 3 megabytes long, text file. So someone actually put that number in, and now there is one unusual thing is you can actually put in to the algorithm, you can create a new file. Let's call it test 2. You can put in algebraic expressions. So for example, suppose I want to put in a prime of the form 2 to the 301 power minus 1. Is that prime or not? So let's save this. And let's load in this file, test 2. And it says that prime that came from this file, test2.in, is not a prime because it's divisible by 127. Okay? Which is what, 2 to the 8th minus 1, or 2 to the 7th minus 1. So you could probably tell from just the structure of that it was divisible by that. So this is a very fast prime number tester. One of the more interesting links, I assume most everybody here has heard of the program called SETI. The SETI program, SETI, stands for Search for Extraterrestrial Intelligence, and you can download a version of it, which is a screensaver, And what it does is it takes unused cycles on your machine and processes radio telescope signatures. So your machine, in concert with maybe hundreds of thousands of other machines, is busy analyzing data, searching for patterns in extraterrestrial signals that originate from outside the solar system. Well, the GIMPS page is, GIMPS stands for the Great Internet Mersenne Prime Search, is the same thing. What you do is you download this piece of software and you contribute to determining whether 2 to the p minus 1 is a prime or not. Now, the largest primes known to man are of this form. And these are called Mersenne primes. So if you look at how it works, that link actually the 5th largest known prime was discovered by this program. The 39th known Mersenne prime is over 4 million digits long. So this guy proved that 2 raised to the 13,466,917th power minus 1 is a prime. And it took a few weeks on this 800 megahertz AMD computer. However, it took over 2.5 years and tens of thousands of computers to test over 100,000 unsuccessful candidates. So he happened to get lucky, punched in a number, and found out that it was in fact prime. So this project has actually found 5 Mersenne numbers already. And these are a list of them. Okay, so this is kind of an interesting group software project. Before we go to the Maple, and I'll go through some of the Maple commands with primes, there's one last link that I wanted to show you, and this is a Maple worksheet, which comes from mapleapps.com, which is just a library of Maple code. And this is downloading tons and tons of GIFs here. So this is the HTML version of the Fermat's Little Theorem, and it's actually a talk given in the format of a Maple worksheet. So it goes through the history of Fermat's, the use of the word little, the fact that although it says it's little, it's quite important. He goes through some Maple commands to tell, and actually some of the ones that we're going to use, like next prime, mod, etc., are built-in commands. Now Maple itself contains a couple of built-in prime commands. Namely, there's a indicator function called isPrime that will return true or false whether a number is prime or not. Also, if you put in a number, you can determine the next prime and the previous prime to a sequence of numbers. And you can also indicate the ith prime. So if you wanted the 1 millionth prime, you could just write a function to do that. So let me fire up Maple and I'll show you how these work. Okay, so if you actually type the command isPrime, and let's just do 1, 2, 3, 4, 5, 6, 7. This will return with either true or false, depending on this expression. So in this case, it's false, so you could factor this. In fact, there's probably a command called factor. So let's see if we can actually factor this expression into I guess not. There's actually, the ith prime, so if you want to know what the 1000th prime is, it's 7,919. If you want to know what the 10,000th prime is, oops, if you spell it correctly. It's 104,729. And actually, you could verify the prime number theorem that says that the number of primes less than n looks like n over log n, or there's a formula for it. So in fact, I guess if you did 104,729 divided by log 104,729, you get roughly this. So it's not quite exact, but it's close. So if you want to say, what's the next prime after 100,000? Then it says, okay, 100,003 is the next prime. If you want to know what the previous prime was, it's 99,991. So Maple has at least 3 or 4 actually, is prime, ith prime, next prime, etc. Let's put that in here. Okay. I think that will pretty much wrap up what I wanted to do today. Just to summarize, these are just a lot of links. We obviously haven't gone through many of the links. There's a lot here. But people have played around and puzzled over primes and their properties since, Euclid's time. And there still actually is room for discovering new properties of primes, and the finer details of the distribution of primes and predicting whether a number is prime or not and factoring large integers actually has very practical effects, because we saw in a previous lecture that the prime factorization has to do with the security of modern encryption algorithms. Okay, so I think with that we're going to end today's